The transmission acts as the power manager for a superbike. It is responsible for regulating exactly how the engine's power reaches the rear wheel. By selecting different gear ratios, the transmission balances the trade-off between explosive acceleration and high top speed. Most importantly, it allows the engine to operate within its optimal RPM range, ensuring the rider has access to maximum power exactly when needed. Most superbikes use a 6-speed sequential gearbox. Unlike car transmissions, which use a complex H pattern, sequential boxes shift in a fixed, linear order. This design is optimized for high-performance riding. By forcing gears into a linear sequence, the transmission achieves faster, more reliable gear changes when split seconds matter. This configuration allows the rider to click through gears rapidly, ensuring power is maintained throughout the acceleration phase. Gear ratios determine how power is delivered from the engine to the wheels. By changing gear sizes, we balance the need for acceleration versus top speed. In lower gears, a smaller gear drives a larger one. This multiplies torque, giving you the force needed to launch the bike from a standstill. Higher gears reduce engine strain at high speeds. This allows for increased efficiency and a higher top speed, but sacrifices the rapid acceleration felt in lower gears. Selecting the wrong gear can be problematic. If your gear is too high, the engine will struggle to accelerate. If it's too low, you'll hit your RPM limit quickly, wasting potential performance. A quick shifter relies on a pressure sensor integrated into the shift rod. When you apply pressure to the gear lever, this sensor instantly detects the force, whether it's a pull or a push. The sensor sends a signal to the ECU. The engine controller then cuts ignition or fuel for a few milliseconds. This removes the load from the transmission. With the engine torque momentarily released, the internal dog clutch can disengage and snap into the next gear position instantly, without you needing to pull the clutch lever. This sequence allows for seamless, full-throttle upshifts, keeping the motorcycle balanced and maintaining acceleration through the corner. Auto blippers are advanced electronic systems designed to assist in aggressive downshifting. When a rider downshifts, the engine's RPM must suddenly increase to match the lower gear ratio. The system detects a downshift signal and tells the ECU to momentarily blip the electronic throttle. This perfectly matches the engine speed to the new gear, eliminating rear-wheel hop. This results in seamless corner entries, reduced mechanical stress on the transmission, and improved chassis stability. The clutch acts as the physical bridge between the engine and the transmission, managing the flow of power. When engaged, power flows seamlessly from the engine into the gearbox, allowing the motorcycle to accelerate. Pulling the clutch lever disconnects this bridge, allowing the rider to shift gears without damaging the internal components. Releasing the lever reestablishes the connection, smoothly transferring torque once again. This simple yet essential mechanical action protects the gearbox and ensures smooth power delivery. Inside the clutch, multiple friction plates are stacked together to transfer rotational force. When the pressure plate compresses the stack, friction locks the plates, transmitting engine power to the transmission. When the clutch lever is pulled, the plates separate. The engine can then rotate freely, allowing for stationary idling. The chain drive serves as the final link in the motorcycle drivetrain, transferring power directly from the engine output to the rear wheel sprocket. Engineers prefer chain drives for their lightweight construction and incredible efficiency. They are engineered to handle the massive torque loads produced by high-performance engines. Chains require regular cleaning and lubrication to reduce friction. Neglected chains wear quickly, leading to power loss or catastrophic failure under the high stress of a racing environment. Suspension serves two primary purposes. First, it absorbs road imperfections to improve comfort. Second, and most importantly, it maintains the tire's contact patch with the ground for maximum grip. Front telescopic forks consist of two sliding tubes. As the wheel hits a bump, the inner tube compresses into the outer tube, dampening the energy of the impact. The rear monoshock is a single spring overdamper unit. It manages weight shifts and stabilizes the bike during acceleration, braking, and cornering. By working together, the front and rear suspensions stabilize the chassis, ensuring the motorcycle remains balanced and predictable under varying road loads. Suspension tuning goes beyond simple comfort. It is the primary tool for managing weight transfer during braking and acceleration. When a motorcycle brakes, weight shifts forward, compressing the front forks. Tuning manages this dive to keep the chassis stable. Under hard acceleration, the rear monoshock bears the load. Proper damping ensures the rear wheel maintains consistent grip rather than skipping. By balancing compression and rebound, we ensure the tire's contact patch remains stable, maximizing traction throughout the cornering process. Modern high-performance superbikes utilize electronic suspension to adapt to the road in milliseconds. Sensors constantly monitor speed, lean angle, and braking force. This data is fed into the suspension ECU. The controller commands an electric motor to adjust internal damping valves in real time, optimizing stability and handling. This dynamic interaction allows the bike to maintain the perfect balance between comfort and aggressive performance. A superbike relies entirely on two small contact patches, each roughly the size of a credit card. These patches are the only points of grip between the machine and the road. These small areas are engineering marvels. They must manage massive forces during acceleration, heavy braking, and extreme lean angles. Tire engineering is the single most critical factor for both safety and performance. Motorcycle wheels are precision-engineered components. While aluminum alloy is standard, performance bikes utilize forged magnesium or carbon fiber for extreme strength and weight savings. Reducing unsprung and rotational weight is critical. Lower mass at the rim allows for faster acceleration and significantly improves cornering agility or flickability. By optimizing wheel construction, engineers reduce the energy required to change the wheel's state of motion, resulting in sharper response and better suspension performance. Unlike car tires designed for a flat footprint, motorcycle tires feature a distinct rounded profile. This shape is fundamental to high-performance handling. As the motorcycle leans, the contact patch shifts smoothly across the rounded shoulder. This transition allows for a consistent grip at extreme lean angles. Tire performance is defined by a constant trade-off between grip and durability. Manufacturers manipulate rubber compounds to suit specific riding conditions. Soft compounds possess high polymer flexibility, allowing them to conform to track surfaces for maximum traction. However, this elasticity causes rapid molecular degradation under heat and stress. Conversely, hard compounds utilize denser molecular structures. This rigidity generates less heat and wear, making them ideal for endurance riding, albeit with reduced mechanical grip. By selecting the right balance of polymers, riders can optimize their setup. Soft rubber provides the confidence needed for high-speed corners, while hard compounds ensure the tire survives the distance of an endurance event. Tires are designed to function within a specific temperature range. When cold, the rubber compound is hard and lacks the molecular flexibility required to conform to the road surface. As the tire warms, the rubber compounds soften. Heat increases molecular movement, allowing the rubber to deform and interlock with the road surface at a microscopic level, creating grip. This is why professional racers perform warm-up laps. They are essentially charging the tires with energy until they reach their optimal operating state, where grip is at its absolute peak. Stopping a motorcycle from 300 kilometers per hour requires robust hardware. The primary components are the ventilated disc and the multi-piston caliper. The system converts massive kinetic energy into heat through friction between the pads and the disc. Brake fade occurs when intense heat compromises the braking system's ability to stop the vehicle. Repeated heavy braking on a racetrack generates extreme temperatures in the discs and calipers. The primary cause of fade is the boiling of brake fluid. When fluid reaches its limit, gas bubbles form, which are compressible, resulting in a spongy lever feel and reduced stopping force. Premium systems, such as those from Brembo, are engineered to resist brake fade. These systems use advanced materials and designs to dissipate heat efficiently, ensuring consistent, predictable stopping power under racetrack conditions. Anti-lock braking system, or ABS, is a critical safety feature that prevents wheels from locking up during emergency stops. Sensors monitor wheel speed thousands of times per second. When the system detects a loss of traction, it immediately intervenes. The system modulates brake pressure, rapidly pulsing the hydraulic force to allow the wheel to keep turning. By preventing lockup, ABS allows you to maintain steering control, drastically reducing the risk of a crash. We have completed our deep dive into the mechanical heart of the machine. We've explored how raw power is produced, how it is transferred through the gearbox, stabilized by the suspension, and finally brought to a halt by the braking system. Our mechanical journey is now complete. In the next series, we shift our focus to the hidden technologies that control these systems, the electronic brains of the motorcycle. We will cover sensor networks, control units, and the complex algorithms that define modern performance.